Hello students. Welcome to the YouTube channel, Physics Simplified. Here, we will understand numerous concepts of physics from a numerical perspective. So, without any further delay, let's jump into the discussion. Topic of discussion for today's video: magnetic field due to straight line currents. This is another application of Biot-Savart Law. In this problem, we have two long straight parallel wires separated by 100 centimeters. Out of these two, the wire on the left carries a steady current of 6 amperes. The direction of this current is into the paper. In the first part of the problem, we need to find the magnitude and direction of the steady current through the wire on the right, such that the net magnetic field at the point P becomes zero. Knowing the current in the wire on right, we need to determine the magnitudes and directions of the magnetic fields at points Q and S in part B of the problem. Let us now identify the concept required to solve this problem. We know that the flow of current through a wire develops a magnetic field around it. Hence, to determine the total magnetic field at the given points, first we need to calculate the magnetic field produced by each long straight wire at those points for the flow of a steady current through each of them. The formula required is given by B is equal to mu0 I divided by 2 pi r, where mu0 is the permeability of free space, r is the distance of the given point from the current carrying wire. The direction of the magnetic field produced by each straight current carrying wire at each of the given points can be determined by using the right-hand rule. Addition of these fields will give the total magnetic field at the given points and other necessary information. Let us now set up the first part of the problem. According to the figure, the direction of the current I2 must be into the paper in order to get zero magnetic field at point P. Let me explain why. First, we consider the direction of the magnetic field at P due to current I1 through the first wire, that is, wire on the left. The magnetic field lines for a long straight wire are concentric circles with the wire at the center. The magnetic field at each point is tangent to the field line as per the right-hand rule shown in the figure. So, vector B is perpendicular to the line from the wire to the point where the field is calculated. When the current I1 is into the paper, the direction of the magnetic field, vector B1, at point P is due south. We consider the magnetic field at P due to the current I2 as vector B2. Now, to make the resultant field at P 0, the field vector B2 must balance the field vector B1. That is, vector B1 and vector B2 must be equal in magnitudes but oppositely directed. So, the direction of the field vector B2 due to the current I2 at the point P must be towards north. This is only possible when the current I2 through the wire on the right is out of the paper. Let us now calculate the strength of the current through the second wire, that is, wire on the right. For the first wire, strength of current I1 is 6 amperes and the distance of the point P from the wire given by R1 is equal to 150 centimeters, that is 1.5 meters. For the second wire, the distance of point P from the wire given by R2 is equal to 50 centimeters, that is 0.5 meters. By using the expression of the magnetic field due to a long straight current carrying wire, we get the expressions of B1 and B2 as follows. The unit for both the magnetic field is Tesla. Since B1 is equal to B2, hence, equating the two expressions and simplifying, we get I2 is equal to 2 amperes. So, the magnitude of I2 is 2 amperes and it is directed out of the paper. This is the answer to the first part of the problem. Let us now calculate the net magnetic field at point Q due to the currents I1 and I2. Using the right-hand rule, we find that the magnetic field B1 at point Q due to the current I1, which is into the paper, is due north, while the magnetic field B2 at point Q, due to the current I2, which is out of the paper, is due south. For the first wire, strength of current I1 is 6 amperes, and the distance of the point Q from the wire, given by R1, is equal to 50 centimeters, that is, 0.5 meters. For the second wire, strength of current I2 is 2 amperes, and the distance of point Q from the wire, given by R2, is equal to 150 centimeters, that is, 1.5 meters. By substituting the values in the expression of magnetic field due to a long straight current carrying wire, and simplifying, we get the magnitudes of B1 and B2 as follows. B1 is equal to 2.4 into 10 to the power minus 6 Tesla, and B2 is equal to 2.67 into 10 to the power minus 7 Tesla. Since B1 and B2 at point Q are oppositely directed, and B1 is greater than B2, the net magnetic field at Q is obtained by subtracting B2 from B1. Therefore, the magnitude of the net magnetic field at point Q is given by B suffix Q is equal to 2.13 into 10 to the power minus 6 Tesla, and is due north. In the final part of the problem, let us now calculate the net magnetic field at point S due to the currents I1 and I2. Again, using the right-hand rule, we get the magnetic fields at point S due to the currents I1 and I2, as shown in the figure. For the first wire, strength of current I1 is 6 amperes, and the distance of the point S from the wire, given by R1, is equal to 60 centimeters, that is, 0.6 meters. For the second wire, strength of current I2 is 2 amperes, and the distance of point S from the wire, given by R2, is equal to 80 centimeters, that is, 0.8 meters. By substituting these values in the expression of magnetic field due to a long straight current carrying wire, and simplifying, we get the magnitudes of B1 and B2 as follows. B1 is equal to 2 into 10 to the power minus 6 Tesla, and B2 is equal to 5 into 10 to the power minus 7 Tesla. According to the figure, we find that the triangle is a right-angled triangle, subtending an angle 90 degrees at point S. So, the two field vectors, B1 and B2, are mutually perpendicular. Hence, the magnitude of the net magnetic field at S is equal to under square root B1 squared plus B2 squared. Here we have used the expression of the resultant of two mutually perpendicular vectors. Now, substituting the values and simplifying, we get B suffix S is equal to 2.06 into 10 to the power minus 6 Tesla. If we consider B suffix S makes an angle alpha with B1, then alpha is equal to tan inverse of B2 divided by B1, which is equal to 14.04 degrees. So, the net magnetic field at point S is 2.06 into 10 to the power minus 6 Tesla, and is inclined to an angle 14.04 degrees with B1.